Prof to give his talk, which I don't know what it's about because the title is not there. Anyway, John King from Nottingham, doing multiphase stuff, I think, if I remember.
That's right. Thank you, Mark. So I'm going to do this talk on the board. I'm not going to attempt to cover anywhere near as much ground as Mark. I do want to do it on the board because I want. Where's the switch? I'm not going to attempt to cover nearly as much ground as Mark, but I do want a lot of the details I say to be comprehensible to the majority of the audience. So please interrupt where I fail, or if I'm illegible. Remember, I'll be facing the board some of the time, so shout out. So my title was Multiphase Modelling of Cells and Tissues. It'll probably be clear from that title that I didn't, when I gave the title, I wasn't sure what I was going to talk about. I'm not going to talk about specific biological applications. I came to the conclusion I didn't want to, but also I've been spending a lot of time on plants recently, which makes it rather hard to talk sensibly about cell motility. So I'm going to talk about some fairly general multiphase frameworks. Multiphase has been used in two different senses at this meeting. One sense, and actually, as far as I can judge, the most common sense is where interfacial cases where you have two materials separated by an interface. You may make that interface diffuse. That's not the class I'm talking about. I'm going to talk about the class where the different phases coexist in at the same point within the abstract mathematical framework. So let me mention the biological applications we have looked at because it may help explain what I've just said. So one is individual cell motility. So that's modelling at the whole cell level, not trying to capture the details of the individual cell components. And there the individual phases might be cytoskeleton and the cytosol. Okay, so in interpenetrating phases, the cytoskeleton, of course, extremely complex in particular, so one wouldn't want to, at this continuum level of modelling, one wouldn't want to capture the details of that through interfaces. One wants to smear out average across the scales, much less than the scale of the whole cell. So the other applications we dealt with is tissue growth, so both cancers and tissue engineering. So that's at the whole tissue level. And there the phases might be, although this is not what I'm going to do, the cells and the extracellular matrix. And of course one can add any number of additional phases, so in particular if you want to do stem cell differentiation within a scaffold, you'd need different cell types. The final case I can remember having done is biofilm growth. And again, that's at the whole biofilm scale, and then there will be cells and, for example, extracellular polymeric substances. Okay, so those are the kind of applications we've looked at. Let me now get straight to the starting point of what I want to talk about to indicate where I'm going. The simplest, I'm going to concentrate on the tissue growth case. So incidentally, where I use specific jargon, it'll be kind of associated with the tissue growth context, so similar things apply to the others. I'm going to work in 1D because that means I can do much more on the board. Quite a lot goes over to higher dimensions, but there are some fundamental additional issues in higher dimensions that I'm not going to touch on. So what might a model for tissue growth look like? Well, the very simplest candidate would be that one. So this is the cell motility bit, so that's cell random motion, diffusion of cells, and this is cell division. And I'm going to think only about the simplest case where the division rate K is a constant, so all cells present are dividing. I need to define what N is. N is going to be the cell volume fraction, which means it's going to have to lie between 0 and 1. Okay, so 1 is when the whole region is occupied by, the particular point is fully occupied by cells. 0 is where none of it is. Okay, so there are at least two difficulties for this equation in terms of the things I want to say. And the first is this doesn't prevent, in fact it ensures, that n goes above 1. Again, there's various ways to see that. The simplest is to note that you can factor out the e to the kt and observe that for large time the solution looks like the heat equation solution growing like e to the kt. Okay, so diffusion to some degree reduces the cell levels. The thing is smearing out under diffusion, but cell division is driving growth much faster than that's causing decay. So that thing automatically grows much bigger than 1.
So are you taking K to be positive?
Yeah. Although I'll mention some, that's actually going to be my second point. So for this comment, K is a positive constant. Okay, so what's the traditional remedy? Is to add a single extra term, which prevents that happening, and that gives you Fisher's equation. Okay, so that blocks n going above 1. So, but my complaint about this equation is, what does this thing mean physically? Okay, it's very commonly done, including with much more complicated models of this type. But what does the minus n squared term mean? So has anybody got any offers? Yeah.
It could come from homeostatic pressure.
Mm-hmm. I'm not sure that would sit in the source term, but I'll have a pressure later, and maybe you'll want to come back to that comment.
For spheroids, actually, it has been shown that the division rate decays linearly with the cell density. So you could
yeah, so contact inhibition is probably the immediate argument one would think of. I'm going to exclude that, and I would appeal to Mark's first video to do that. So ordinary cells are contact inhibited, cancer cells aren't, and you saw in Mark's video that although the cells were essentially close packed, they were still dividing happily, right? So I'm going to exclude, I'm going to think in just, if you like, in abstract terms, that's not, you can't appeal to contact inhibition to give that, although if you specifically want to model contact inhibition, you may well do that. Any other comments? Yeah.
Well, there's typically a stress effect on growth of some sort.
Yeah.
That experiment.
So one can make K depend on P, for example, the pressure, but that to shut it down that way, but that wouldn't explicitly be an independence. No. They're all sensible comments. I'll maybe come back to them because I'm going to have pressures and things later. Okay. So what's my other complaint straight away? Well, this conference is supposed to be partly pattern formation. So cell aggregation, for example, if you're going to describe it by a model like that, you're going to take D to be negative. Okay. Sorry, you asked about K. I should have said D. So if D is negative, this corresponds to a backward heat equation. So it says it makes no sense mathematically. So that's ill-posed. So in particular, although it will cause the cells to aggregate, they'll come together rather than spreading apart with negative D. The solution will cease to exist in finite time. Okay, and the remedy for that, the most usual remedy for that in material science at least, is to add an extra fourth derivative term. Okay, that does the trick. The multi-phase models I'm going to talk about later give you a different regularization with rather different mathematical properties, and that's one of the things I want to emphasize later.
If you recall physics, what is missing is elasticity.
I'm going to come to continuum mechanics shortly. Yeah.
So what does that term mean?
So you can think about this as long-range effects. So I mean, in material science, it's to do with atom-atom bonding, right? I'm not because I'm not going to have this regularization. I'm not going to try and give it a biological meaning, but it does the mathematical trick of making this a sensible model, and will pattern form. The cells will aggregate into clusters.
Are you thinking of this on all of R, or are there boundary conditions?
Either. So I am going to be rather vague in places. Is there something specific behind your question? No. Okay. So multi-phase. Right, so the crucial equation I'm going to repeatedly have is the following, which we have seen before in Dagmar's talk. So if one has a velocity field within a growing tissue and it's dividing, that's what the equation would look like. Okay, so the first equation I wrote down does correspond to that. If you do a thermodynamic argument where you have diffusion down a chemical potential gradient, so this is an entropic argument, you'd have a diffusive velocity field that's minus d. Sorry, I've gone to higher dimensions. You'd have d times the gradient of log n, which would give you precisely the equation on the right. So this equation does embody the one on the right as a special case. Right, so it's the very simplest class of model I want to deal with in the multi-phase case is to have a second phase, which I'll call E, and might as well just be empty space. So I'm going to add the second equation for the second phase, so this is extremely abstract. So those are two equations. There are three unknowns still, but the third equation is a medium, which is everything. These are volume fractions, so they have to add up to 1. Everything must be one or the other. So to see how that relates to the Fisher business, I'm going to add the two equations together and determine the velocity field. So add those two together, because n plus e is 1, those things add up to 0. The things inside the convective terms add up to 1 as well. So you end up with dv by dx is kn. Okay, and then when you differentiate out this term and stuff one of the terms over onto the right-hand side, you've got dm by dt plus v dm by dx. It's precisely the Fisher term, but for a completely different reason. Okay, so if you move with the cells, if you move with the cellular velocity, which is what this time derivative on the left-hand side is about, you're guaranteed that n never gets above 1. Okay, so by these kind of velocity arguments, you immediately get away from the difficulty of n getting bigger than 1 without appealing to any biology at all, which I think you need, right? So,
you have same velocities for both fields and then
yeah. So this is the very simplest case. I sort of think about this as being 1.5 phase. So the empty space is being carried with the cells. I'm going to have two velocities in a minute. Okay. Okay, so at this point I am going to write down the model I'm going to work with throughout. Using the piece of paper to make sure I get the notation right. I want to keep it up here. So if I start rubbing it out, can somebody tell me? So I'm going to have the same equation for n that I've already written down, but I am now going to have two velocity fields, so there's going to be a Vn there. For most of the talk, I'm going to do a very idealized case where the two phases are cells and water, and I'm going to miraculously make new cells out of water. So I'm going to conserve overall mass, right? So there's going to be a minus Kn on the right. So importantly, in terms of the last question, I have now got a distinct velocity field, Vw, in addition to the original cell velocity field. And incidentally, because you're making new cells from water, the velocity fields have to be in the opposite direction. The tissue has to suck in water to make new cells. And that again is to do with this mixture theory business. At the same place, you've got to have these things having different signs. So the other type of multi-phase model is not appropriate. Okay, again, I'm going to have the no voids thing, that everything has to be one phase or the other. Okay, so that's mass. The other thing is momentum. So this is where mechanics is now coming in. So there's various equivalent ways to write these things, and I think I'd vary through the years, but I'll try and stick to the following for the time being. Okay, there's going to be extra terms in a minute, but that's the momentum equation, part of the momentum equation for the cells. Then correspondingly for the water, I'm going to take the water to be inviscid. This tau n is the non-hydrostatic part of the stress for the cells, so that'll be non-zero much of the talk. Okay, and again, there's a different pressure for the cells than there is for the water. So these first sets of terms are the intraphase terms. Okay, it's how the cells interact with the other cells, or how the water interacts with itself. And then there's the interphase terms. So there are two of those. There's the friction between the cells and the water. So that's usually done by a Darcy expression, that the velocity difference gives you the frictional effect between the two, and then there's a force exerted between the two, and that's at least in this type of model I'm concerned with, that takes this form. So Pi is some interfacial pressure. It's the pressure that sits on the interface between the two phases, multiplied by the gradient of their volume fractions. So these are the interface terms. So how the two phases interact with each other. So because of Newton's third law, these force terms of interaction have to add up to 0, equal and opposite reactions and things. And they do indeed, because m plus w is 1. So you add those two together and you get 0. And since we're here, I'm going to underline Newton. And that's Newton's third. Okay, so at this point, I need to count variables. Well, at the moment, I've got, 1, 2, 3, 4, 5 equations. The unknowns, I've got two volume fractions, 2 velocities, that's 4. There's 3 pressures, and there's 1 stress. So I'm short by 3 equations, so I need to give 3 constitutive equations to close the system.
So you're assuming the velocities are known as well?
No, so, right, recap, there are, the variables in here are two volume fractions, 2 velocities, I need to know all of those, 3 pressures, and 1 stress torr. So I think that was 7, did I say? So I'm 3 equations short still, which I'm about to write down. Okay.
Question?
Yeah.
Can you elaborate on this interfacial stress?
Yeah, so I have to say, I find the multiphase literature quite opaque. The simplest way I think about this is suppose an ideal situation where you have all your cells like that for some reason. If there's a pressure sitting along there, it's going to have a net effect there, so it's down the gradient of cell concentrations. Does that help?
Well, except you've got your cell and your water phase coexisting at every point in space.
Yes, I know.
So how would you go from this description to that local description?
Well, one answer to that is with a lot of work. So non-Druid people do all these averaging approaches, right? I don't think I can give a more satisfactory answer immediately. Yeah, there's another way to think about it, which I'll come to in a minute, which is you don't want a gradient in n to drive a flow per se. So these things are both in terms of the hydrostatic pressure. So these things will both have a hydrostatic pressure in. That the n derivative bit has to be cancelled out by something, and it's that bit.
So why is the subscript I?
For interfacial. Yeah. Okay, so I need my 3 constitutive assumptions. So the one I'm going to use throughout is the simplest. So I'm going to take torr n to be a Newtonian fluid. So I'm going to think about timescales that are sufficiently long that you can think of a tissue as a fluid, and that may be very dubious. Elasticity is much harder, and we've heard about even more complicated constitutive relations. But this does have the virtues, I can call it a Newtonian fluid. And all that said, I can't resist pointing out that Newton did all his clever work at Woolsthorpe near Nottingham, not anywhere else you might think about. Right? Okay. So, that means I'm still 2 equations short, and the relevant 2 are constitutive assumptions relating the 3 pressures. So the ones I'm going to write, I'm going to take that just defines P. P is going to be the pressure in the water for ease of notation, so that's the hydrostatic pressure. And then I'm going to take the other 2 pressures, the pressures within the cells, to be hydrostatic. It's got to respond to its surroundings, but it might do something else as well. So there's an extra pressure, which for my purposes I'll take only to be a function of the cell volume fraction. And I'll do the same for the interfacial pressures. So one way I think about those 2 extra terms is cell-cell interactions, catarins or whatever you might want to put in here. If the other phase was a substrate, the ECM or something, you might want to put integrins in here, but those 2 extra bits have to do a lot more work beyond that. But you can start to think about what their meaning might be in a multi-scale biological context. Okay, so that's the full system. And I'm going to do various simplifications of it.
John,
Yeah.
just to add a comment to the questions that was done before, there is a thermodynamic argument that tells you that from that constraint, the geometric constraint over there, W plus N equal 1, there must be a common pressure, which is a Lagrange multiplier that appears there, the common P, and that appears in the two terms, in the stress and into the interfacial force like that.
Yeah, well, that was going
Right.
to be another question, why those two pressures are different.
Why this one's different from
You're saying
that?
they're the same, right?
Yeah?
You're saying that
There is a lambda, there is a multiplier, which should appear in both terms like that, in that form precisely. Now, whether you take the sigma n inside the PI or PE or inside the stress contribution is a matter of choices in some sense.
Yeah, so P enforces overall volume conservation, which is actually about the thing I'm about to write down. So let me do that. So you can give at least a partial variational derivation of these equations, in which P would be a Lagrange multiplier. So if I add the first two equations over on the right together, that's the overall volume constraint condition. I'm going to think about a symmetric case, so both velocities are 0 in the middle. So it's going to be that. And you're immediately seeing hints about why I'm only doing one dimension, because in terms of these kind of manipulations, the thing becomes much more complicated. There's also an overall stress result, which comes from adding the two momentum equations together, and that ends up being there's a p by dx. If you work through all the, I'll get this wrong, so let me check my notes. No, sorry, I haven't. The easier way to do it is not to back substitute the constitutive equations yet. So it's d by dx npn plus wpw. So the interphase bits cancel, as they have to. I appeal to Newton again. And then plus d by dx of n mu n dvn. Sorry, I've forgotten n at the top. Equals naught. So incidentally, that's the thing I promised earlier. The velocity fields have to be in opposite directions. And this will give me npn plus wpw is the viscous stresses. Okay. So one can strip the model down significantly already. I'll use that more explicitly in a bit. There's one other thing I want to do, which is to give expressions for the velocity fields that may be more recognizable from other contexts. Okay, so what are the simplest expressions to deal with in terms of the velocity? There's the middle equation there, the overall conservation mass equation, and then this second equation, this bottom equation rather, over on the right, which gives you VW in terms of Vn, so you can eliminate between the two. And the equations I end up with from those two equations are the following. And the reason I'm writing them down will become clear in a second. So that's the water velocity in terms of the various other quantities. So one can explicitly eliminate some of the variables in favor of the others in one dimension. And that's the cell velocity. Okay, and the reason I'm writing that down is it's the sum of two terms. And if you're used to mechanics, you'll recognize this term. That's the Darcy velocity, flow down a pressure gradient. And this is a Fickian velocity, so flow down a concentration gradient. Okay, but the second term isn't just random motion. You can include random motion in it in the way I alluded to over here, but it can have a lot of mechanics in it as well, how the cells are interacting mechanically. Okay, so that's the model I'm going to work with almost throughout the talk. I may do one slightly different one if there's time at the end. I'm going to do two types of simplification, further simplification to that model, and then I'm going to talk about the kind of mathematical structure of that full model and how it relates to other pattern forming systems. Okay, so the first simplification I'm going to do is kind of wild one where I'm going to completely throw away the viscosity of the cells. So I'm going to treat even the cells as an inviscid fluid. Okay, so that's going to reduce the order of the system because I'm not going to have the extra, I can't see them anywhere here, they're at the top, the extra derivative of the velocity field. Okay, so what happens now? Well, the most insignificant thing is that thing disappears. so NPN plus WPW is 0. Then remember, I'm expressing these constitutive assumptions for the various pressure fields in the middle of that top board. So that's just P, that's P plus something else, N plus W is equal to 1. So that ends up being P. The hydrostatic pressure is related to the cell-cell interaction pressures according to that formula. Okay. So what then is left? Well, I can now evaluate Vn because I now know P in terms of N. This is prescribed in terms of N. W is 1 minus N. So Vn is going to be, for the record, I'm going to only do this once. I'll write it down in full. There's the Darcy drag term. There's these various 1 minus N's because that's W. There's a d by dx n sigma of n, which is that the Darcy term over there, which is now turned into a Fick-like term because, again, it's down the concentration gradient. And then there's the term I originally described as Fick, which is, again, still Fick. Changes sign because n is 1 minus W. So if you differentiate this out, this thing is some nonlinearity times dn by dx. So I can define that whole thing to be d of n over n dn by dx. So we're almost back at the very simple model I started with. So finally, dn by dt is d by dx. You've now got a single equation just involving the cell volume fraction, which is that one there. Okay, so I have gone from my original linear reaction diffusion equation, which I objected to because n got bigger than 1. I've non-linearized it. One way of non-linearizing it is through Fisher, which is there. But this pseudo-mechanical argument gives a different class of non-linear location for the non-linearity, which is in the diffusivity. So I now need to talk about how that can help you. And also, incidentally, to link this back to the very earliest tissue, I think the very earliest tissue growth models of Greenspan and so on, where one...
In your transformations, do you also deal with the boundary condition? Which you haven't studied any,
right, so I complain when people don't give boundary conditions, so it's a fair comment. So here, I'm thinking about the symmetric case, though. Velocities has to be 0 in the middle, right? So that's that. This case corresponds to the edge of the growing tissue. Both stresses have to be 0. So the constant integration is 0 there too. And I don't think I've done any other integrations. So under those kind of circumstances, this is the system you end with. Okay. Right. So there is an alternative way of getting to the same system, but I'm going to call it a derivation in inverted commas, because I don't think it makes an enormous amount of sense. But it is used historically, and that just says adopts Darcy from the start, which is what Greenspan and others did. And I'll get to in a minute how I think that relates to this type of modelling. So it says the velocity field is minus some permeability, which may depend on n, times the capital Pn by dx, which is sort of related to my little pn with the cell pressure. So to be clear, this is not what Greenspan did. Greenspan hydrostatic pressure will come to shortly. So prescribing the cell pressure Pn to be a function of n gives mathematically the same formulation I've just written down, if you use that as your starting point. Okay, so, and I'm now going to use this notation because mathematically it is equivalent. The system you get to is equivalent to this one. So what's the sensible way to think about the cell pressure Pn? Well, there's a close packing density, which I'll call phi, which in the simplest case you think about, you take phi to be 1, but cells can't actually get that close together. So this is the cell volume fraction. This is how the cells interact. Okay, well, if you want the very dilute behavior where cells are not interacting with each other at all to be diffusive, you'll want Pn to be proportional to log n as n goes to 0. So that's the diffusive velocity field I've alluded to earlier. But in this class of model, you need to stop the whole point of, well, part of the point, a large part of the point of this was to stop n going above the close packing density. So the way you achieve that mathematically is there's two ways to do it. Either you do that and make the pressure field blow up as you approach phi, or you have the pressure field hitting phi at a finite point, which gives you what's called a complementarity problem, which I'll describe in a minute. So you can alternatively formulate it as the cell-cell pressure increases as you try and push the cells closer and closer together. And then when the cells are close packed, you can get them to close packing, but then the pressure can just adjust itself to whatever value is needed to sustain the level at the close packing level and not a higher one. Okay, so my notation there will be P star, and I'll have that in a minute. So the second of those leads to a free boundary problem. So a situation where there's some region of cells which are close packed. So n is equal to phi, but p is unknown according to that picture. And a second region where the cells aren't close packed, where p is given by the formula, p is given by this prescribed function, pn. But n is free. So in one case p is free, in the other case n is free. So the overall situation you have is the following. I'm going to write this in higher dimensions because I think it's sort of easier to actually see what the content of the model is if I do that. So this is going to be my close packed region. So n is going to be phi in there. The complementarity says that for n equal to phi, p has to be bigger than p star. So that'll be the bit inside. The complementarity bit here will say p is the prescribed function, pn of n, but now n is less than phi. So those are the two different cases you have, the close packed cell cluster in the middle, the more dilute region outside. Okay, so right, I've changed notation. So where p is unknown, I can't prescribe it to be a known function pn, so I'm just going to call it p here. Right. So here we've got divergence. We've got div of v is given by the growth rate, which is going to give you that formula there. So that was essentially Greenspan's starting point. You prescribe the velocity field via Darcy, and then you have an additional growth term, which makes it a slightly non-standard problem. You can't derive this model follows from this derivation in inverted commas I've given. It's not the higher dimensional generalization of the way I derived this n equation. You wouldn't get this. But I'm recording it for those who might be interested in free boundary problems and things. So outside, we've got the m by dt is given by the reaction diffusion equation. So d of n is known in terms of the other quantities, kn. And then on the inside of here, we've got p is p star. On the outside of here, we've got n is phi. And then the final condition tells you how, essentially, you need the third condition here to tell you how fast that interface between the two is moving. And that follows by a conservation of mass argument at that interface. And for the record, it says the pressure field, the normal derivative of it as you approach from the inside, is related to the normal derivative of the volume fraction as you approach from the outside. Okay. So that, I think, is the simplest higher dimensional problem of this class. There's one further, that said, there is one further simplification you can do, and that's not an unreasonable one. And it's the sort of thing that Lamman and Pleas and so on thought about, which is when the cells are not close packed, they're unable to sustain any pressure at all, and that means my d of n is equal to 0. Okay, so in that case, let me draw that again. So that's just dm by dt is k of n outside. It's a singular perturbation. You've got rid of the diffusion term, and that means the free boundary conditions end up being completely different. So one can explicitly solve for n outside by integrating. The equation inside is the same as before. And again, I'm writing this down for people interested in free boundary problems because this is, I think, quite an interesting one and what's known about it. So it's essentially a one-phase one because you can solve for n outside by that formula. And the second free boundary condition is a Stefan-like condition, but with an extra effect to do with what the level of cells outside is. So Qn is the outward normal velocity of that free boundary. And for the record, the whole thing looks like that. So it's a Stefan-like condition, but it involves the cell volume fraction just outside that n plus, and n is now discontinuous at the free boundary. Okay. So that, I think, is all I wanted to say about, no, there is one other thing. There's a mathematical digression I could make if there is time, and I don't think there will be. I would come back to it. But to come back to my little hobby horse about stopping n getting bigger than the closed pack level. Okay, I mean, with these systems, you can see how it happens. Outside n is growing to the closed pack level, but as soon as it reaches it, you move from this dilute region into the closed pack one, and then it stops increasing. Okay, if I go more abstractly back to this general form d of n and compare it with the Fisher version, how do I choose d of n to stop going above the closed pack level? I need d of n to be singular. So I need it to be alpha, and then the obvious assumption to make is that it grows algebraically as n approaches 1. So there's a mathematical question. For what gamma? I think I know the answer to this question, but it's not immediate, and I don't know if there's any mathematical literature on this type of thing. For what values of gamma does n reach phi in finite time if it's less than phi everywhere initially? Okay. And to rewind then, again, this contrasts with the nonlinearity associated with Fisher. I think the model nonlinearity for this system, again, is not to put a 1 minus n in the reaction term, it's to put a reciprocal of 1 minus n in the diffusion term. And that stops your problems. Okay. First simplification, I'm going to do one more. Anything before I move on?
Actually, I have a question.
Yeah.
And it goes way back to your beginning equation. Why do you not want to put the limitations of other forces, etc., into the growth term at the outset? Because that would absolve all these problems, wouldn't it?
Well, no, because if you're going to start thinking in terms of pressure fields and things, you have to write down equations for them. So you could do it by making k a function of pressure, but this is simpler, right? Because I'm still taking k to be a constant, and I would have to go through the same manipulations to get a self-consistent model with k depending on p. I'd still need equations for p.
Some of your end results on the diffusion having to blow up in certain ways, etc., would not come up, right?
Right, but this kind of reasoning tells you that the pressure doesn't just tell you how the you have to prescribe in advance how the growth rate depends on pressure. I would argue this is more first principles, that the cell-cell repulsion, if you try to cram them too close together, is always going to stop them. Let me say it a different way. Even if you could cook up a system where k didn't depend on p, that's a perfectly sensible problem to think about. Right? It may not be biologically reasonable. Yeah. Okay. So my second simplification is much quicker to talk about. And that's the kind of thing we were doing in the tissue engineering context, which is to take W to be much less than 1, which means N is approximately 1. So you kind of think about narrow channels in the ECM the water's getting in through. Most of the volume is occupied by cells. To have self-consistency, you've got to get the water in fast. So you need the velocity of the water to be much bigger than that of these cells. But that's actually immediate from the relationship I think I've rubbed out, which is W times VW plus NVN has to be 0. Okay, so with those, in that limit, the N problem decouples from the W one and gives another system, which I like and I don't think much has been done on. So this is the Stokes flow version of, if you like, Greenspan's Darcy model, initial model for the simplest case of tumour growth. Okay, so again, because it's maybe easier to see the structure, I am going to higher dimensions now, and in this case it is legit, it does follow from the original modelling assumptions. So this is now a closed system for Pn and Vn. It's Stokes flow for the cells. It's completely standard fluid mechanics with the single exception that you're making new material. There is a K there. So although it's very close to classical fluid mechanics, I don't think much has been done with this problem. And in particular, of course, it's again a free boundary one, that if you have some interface between tissue and non-tissue, you'd have to solve this thing in a moving boundary. So that's the end problem. And as I say, that decouples, and then you're left with the W problem you have to solve afterwards if you do want to compute what the water is doing. And in particular, you do actually then have to check that W is positive. This one, unless you do more work, does not guarantee that the cell volume fraction stays less than 1. It's close to 1 by assumption, but could be slightly bigger. And for the record, that's the system for the water. Okay, so Stokes flow for the cells. For the water, if you back substitute the velocity field into there, you've got a convective term driven down the pressure gradients associated with the cells, and then a diffusive term for the water as well, to do with the interfacial effects.
So where did the approximation that VW has to be much bigger than VM come from?
One way of seeing that is this relation. The more physical way to say it is because I'm making cells out of water. If there isn't much water there, I've got to bring it in very fast to make the new cells. Okay, and now I go to the full model, and this is where at least I attempt to touch on the pattern forming theme of this workshop and what is it you can program. So recall I mentioned the Cahn-Hilliard thing where you put in the fourth derivative when D is negative to give you a mathematically sensible problem. Here I want to determine what the, if you take the cells to be viscous, what that does in terms of pattern formation. I'm not going to put any nice simulations or anything. I just want to look more at the structure. So this is now the full model. In other words, the one I started with over there with the additional constitutive assumptions. As I've indicated, there's various first integrals you can do associated with overall conservation of mass and overall conservation of momentum. So here's overall conservation of momentum again. And then I'm going to strip the system down to a pair of equations by using those first integrals to do some elimination. So that's the overall momentum equation, the thing you get by adding the two momentum equations on the right together. And then there's an equation I wrote down before for Vn, which I've now taken the Vn bits over onto the right. Okay, that was the expression for Vn as a Darcy bit plus a Fick bit, but I'm now going to use it to eliminate the pressure gradient. Okay, so the full model in its simplest guise, where you eliminate everything you can, is the original momentum equation I've emphasized throughout. The original conservation of mass equation I've emphasized throughout. And then the equation that comes from all mechanics is the following. I slightly lied earlier. This is one other case where I'm going to write down all the details for reference. So there's a nonlinearity D of n, which is precisely the one I had before. So in effect, I've already written down a complicated formula for D in terms of the n dependence of the other quantities. Okay, so the Vn term is the Darcy drag term, expressed eliminating Vw in terms of Vn, gives you this extra bit. And then there's so this is overall momentum, and then there's the Newtonian velocity contribution. Okay. So that pair of equations now, I guess I get even more abstractly mathematical. I might have time to do the final thing, but if not, the rest of the talk will be about that pair of equations. So I now want to think about the case where D can take either sign. So D positive is the usual thing where the cells are prone to move apart, and which in particular they would do if it was diffusion. And D would be negative if the cells want to aggregate together and form clusters. Okay, so the first thing I'm going to do is throw away the cell division. I'm going to throw away that term, so that will be better suited to the cell motility thing, where you try and use this sigma n and sigma I business to drive the cell in one direction or another, and that kind of gets lost in all these nonlinearities. But anyway, mathematically, I'm now going to talk about k equals naught. Okay, so for the virtue of having k equals naught is there's a steady state which has arbitrary cell volume fraction. So I'm going to linearize about n equals n star. So that's an arbitrary uniform cell volume fraction. And I'm going to linearize about v equals naught. Okay. So the usual linear stability kind of argument, which is pretty simple in this kind of context. So v and capital N are going to be small quantities. I expand and only keep terms linear in those two quantities. So the first equation gives you that, remembering k equals 0. Okay. So of this term, as we've heard from Dagmar's talk, is a combined dilution term, which is the derivative of the Vn bit, and then a conveyor belt term, a convective term to do with the derivative of the n bit. In terms of the linearization, it's only the dilution bit that comes in. And then the second equation, naught, is going to be minus v. I multiply up by the lambda factor. D star is d evaluated at n equals n star. dm by dx. And then I'm going to call everything to do with the mu term. I'm going to call it epsilon, which may or may not be small, but if you think in terms of mathematical regularizations, it will be small. Okay, so that's what the linearized system looks like. Probably the most revealing way now to use it is to differentiate the second equation with respect to x, and then use the first equation to eliminate. Right, and if you do that, you get dm by dt plus equals the obvious diffusion term, and then the regularizing term that copes with the fact that d may be negative, you may be in an aggregating regime, is that term there. Okay. So rather than it being a fourth derivative in space, the effect of the viscous contribution is two derivatives in x and one derivative in t. And I'm about to indicate two of the key consequences of that in terms of pattern formation. So the mathematical jargon for that class is pseudoparabolic. So I'm now going to do the obvious thing and separate variables to tell me about stabilities. So I'm going to Fourier decompose in space, and that'll mean, in fact, real exponential growth or decay in time. So if n is e to the sigma t, e to the ikx, we're going to have sigma is minus d squared, k squared, minus epsilon sigma k squared. So the dispersion relation, the growth rate, is minus d squared k squared over 1 plus epsilon k squared. Okay, so if d star is positive, not surprisingly everything is well, all modes decay, but if d star is negative, actually all modes grow. If epsilon is 0, you can see the ill-posedness in the fact this thing grows arbitrarily fast as k becomes large, but this thing does regularize it, it saturates. So as k goes to infinity, that goes to some fixed finite value. So it saturates growth at large k. But, an important contrast to the Cahn-Hilliard stuff, there's no preferred wavelength. I'll draw a little sketch to indicate what I mean by that in a second. Okay, so that dispersion relation looks as follows. There's the wavelength against the growth rate. Starts off quadratic and levels off. So it does that, whereas Cahn-Hilliard will do something like that. So for Cahn-Hilliard, there's a mode that grows at maximal rate. Here, there's no mode you can identify as being the fastest growing one. The shorter the wavelength is, the faster it grows, but it does saturate. There's another difference from Cairn-Hilliard, which this linear argument doesn't give you, and which I'm not going to do. But those who know about things like Cairn-Hilliard is there's no phase coarsening in this system. Okay, so if the thing lumps into clusters, you don't get this survival of the fattest business where the biggest clusters win. They can just sit there in their current form. Yeah.
Doesn't this sort of break down at large K? I mean, if you're going to have a continuum model, you can't have arbitrarily large K.
Correct. But at least it's not ill-posed. So for any specific initial data, you'll see, if this thing works, I'm going to show the only numerical simulations I'm going to show, which shows it clustering into finite-sized clusters. So I'm going to show 3 plots which came from some stuff we did on tissue engineering a few years back. It's essentially this system with a few extra bells and whistles. So one way to think about this system is a competition between cell division. So this is in an aggregating regime where D is in effect negative. So there's a competition between cell division, which is trying to push the tissue out to grow, and cell aggregation, which sucks it back together. And here we did a situation where if you suck it too hard, it'll start to die. So there's 3 different cases. This is where division beats aggregation. So you see the front moving out as a traveling wave. There's a second traveling wave regime where aggregation beats division. So the thing sucks in, but again, there's a nice traveling wave that does it. And then finally, where aggregation is even stronger, you do get the kind of pattern-forming system where the tissue will break up into individual cellular clusters.
Is that the stationary distribution?
No, that's, I suspect the code broke at that point. Yeah. Okay. So that's the linear stability argument. Try and get the mathematical structure. I don't like systems, right? This is still a pair of equations, which in the case of linearization, you can eliminate V in favor of N to get a single equation. I find it very hard to get insight about that kind of system. So I do want to tell you about one extra mathematical trick, which reduces this pair of equations to a scalar equation, and which hopefully makes it easy to analyze. And again, I don't know of any rigorous kind of mathematical analysis of these kind of equations. So I'm going to talk about a transformation which is closely related to one that takes you from Eulerian coordinates to Lagrangian ones. Again, for those of you who know about continuum mechanics. Right, so I'm going to reduce the amount of writing I'm going to do by rewriting the thing with fewer subscripts and stuff. So the system I'm dealing with, again with k equals 0 for the time being, that's the same equation with some subscripts thrown away. This is the overall momentum equation with the nonlinearities written in more condensed form. Okay. So that's the system I would like it if somebody analysed, but as I say, I want to do a transformation which makes it more appealing, at least from my point of view. And that transformation involves introducing a mass variable, which I'll call M. And M is going to be the total amount of mass to the left of the given point x. Okay. So I'm going to integrate the first equation. So the first equation becomes dm by dt. We've done an x integral of that. That just leaves n times v. So you lose the dilution term. You just get left with the convective term. Okay, so that's my equation for m as a function of x and t. And then the only remaining thing one has to do is change variables from m of x and t. So you do a hodograph, so you take x to be a function of m and t. And if you do that transformation on this equation, you get dx by dt is v. Okay. So m is a Lagrangian variable. It moves with the velocity field. So you can think of it as labeling cells. As cells move along with the velocity field, they keep their value of m. So that allows me to write v in terms of x. I can write everything else in terms of x as well. So n is dm by dx. dm by dx is 1 over dx by dm. So I can write everything in terms of that. And what I end up with is dx by dt is d hat So d hat of y is 1 over y squared, d of 1 over y, and so on. Okay, so I do that. I've substituted for v in terms of this Lagrangian coordinate according to that, and then I replaced n by dm by dx, and therefore 1 over dx by dm, and you get this thing here, plus alpha hat dm by dx, d by dx, beta, dx by dm, d squared x by dm squared. Okay, and alpha hat, beta hat, or 1 over y, alpha 1 over y, beta 1 over y, for the record. So the nonlinearities in transnorm space are very simply related to the original nonlinearities. So that is, now we've now gone from a system to a scalar equation. The final version I tend to write down is for differentiating that with respect to m. So if you write y as dx by dm, the nonlinearities, and differentiate, the nonlinearities look less unpleasant, and you get a fairly standard pseudo-parabolic equation. Okay, so at least you can get it to a scalar form. And rather miraculously, that also works even with cell division. So that's the one other thing I want to say about this system. And then the final thing, which I think I will have time to say about, is to kind of bring me full circle back to what was wrong with that original Fisher equation. I'll end up with an equation very like it, but with one extra term. Okay, so with cell division, so k not equal to 0, the only change is as long as k is a constant, slightly miraculously, you can integrate up the mass continuity equation as well to get that, which then means dx by dt plus km dx by dm is equal to v. So again, you can substitute v in favour of x. Have I got the right way around? Yes, I've got the right way around. So you can substitute for v in favour of x and get, again, a pseudo-parabolic equation with an extra convective term now. So again, you can get it to a scalar system. Okay, so that was sort of a mathematical diversion. The final thing I want to do is write down a model for multiple cell types, which is a simple variant of what I've talked about so far. So I'm going to get rid of water. I'm going to go back to the situation where W is small. The thing can get water in very easily to make the new cells. And I'm going to think about multiple cell types. So I guess we originally thought about this in the cancer context, where the two cell types would be cancerous and non-cancerous. You can think about similar things in the stem cell differentiation business, where you'd have stem cells and differentiated cells.
Before you do that, is the behavior of the system the same for K positive and K negative?
Say the first phrase again.
Is the behavior of the system that you have, is it exactly the same for K positive and K negative?
Right, so one, I haven't done a great deal of analysis of, if you mean in the hodograph form, I haven't done much analysis of it. In terms of the numerics we've done of the original system, there are differences because you don't have this driving force from cell division all the time that I showed in the simulations. So the pattern forming stuff is the same, if you like, but the other aspects of qualitative behavior aren't. Yeah. Okay, so my final system, as I said, is multiple cell types. So I now need extra subscripts. So I'm going to have cell types N1 and N2, velocity fields V1 and V2. Again, I appear in my notes at least to have explicitly labelled them. So that's going to be the tumour cells which are dividing. Here's the normal cells which are not dividing. So if you were doing differentiation, you'd have a transfer term between the two. Here I'm going to take the second one to have 0 in it, but they can change the mathematical structure. So that would be normal. Again, we need N1 plus N2 to be 1. I'm going to say very little about this system. You'll be relieved to hear, but say I wanted to close the loop and get back to where I started. And that's what I'm doing with this, and I'm afraid that involves writing down quite a lot in between. Right, so I is not a label for 1 or 2. I is the interfacial pressure again. So P1 is the pressure in cell type 1, and P2 is the pressure in cell type 2. Now they're both cells, so in general I better let them both have some non-trivial stress field within them, which I take to mean Newtonian. Same thing for the second cell type. So now symmetric because we're doing two cells rather than cells and water. So exactly the same form. In fact, I'm even going to stop writing it down. Exactly the same form with the 1 and 2 swapped. Okay, so PI, in this case, I'm going to take the interfacial pressure to define my base pressure field P. And then there's the two extra pressures in the two cell types. So sigma 1 and P2 is P plus sigma 2. Incidentally, so I was getting in trouble for this sort of thing. I should probably have said much earlier, there's a huge amount of work by other people on multi-phase models, including people like Luigi, and I'm not being exactly rigorous in referring to the literature and so on. Right, so I just want to do two things with this. The first is to take the drag between the two cell types to be very large. And that brings me back pretty much to what I had at the beginning. So in the limit that the drag is very large, you just get V1 and V2 both moving with the same velocity field, which in a lot of situations is sensible. If you're not interested in metastases or something, the tumour cells are probably going to push out the normal cells at their own local velocity. Okay, so then we're sort of in territory we've already seen. So for the record, I'm writing it down again. The thing reduces to a pair of equations. That's the one for N1, identical to what I've already written down. Then sum up the two equations together. We got v by dx is kn1. This gives exactly the equation I wrote down very near the beginning. I just want to do one extra thing with it. I'm not being very efficient in terms of writing, I'm afraid. So you get, again, this Fisher-type nonlinear term, but for a completely different reason. The reason I'm writing this down again, I now remember, is I want to note that if you introduce the mass variable again, so n1 is dm by dx, you can express it, you can eliminate v and m in favour of m, and you get essentially the implicit Burger's equation. Okay. So you get a single closed first order PDE, which I regard as the very simplest tissue growth model. It's the one I've written down there. If you know about implicit Burger's, it can form shocks, but because n1 is positive, m is an increasing function of x, so this thing never shocks. Okay, so it does stand on its own as a not completely unreasonable way of describing growing tissue. Okay, then you get P decouples, and the pressure field you work out afterwards. Right, and the very final thing I want to say. So under some circumstances, and I'm not going to justify where they come from, there's a slightly more complicated simplification of that system, which ends up with having the difference in the velocity field being something that looks like a diffusion term. Okay, so you get that difference. Then again, if I go to m coordinates, I end up with a single scalar equation, and that's the thing I want to finish with. That's sort of my punchline. So if you work through all the details, there's one equation relation V1 and V2. There's the overall conservation of mass equation, gives you a second relation between them. If you do all the elimination, the equation you end up with is the following one. You get the terms from the implicit Burger equation I wrote down a minute ago, but there's one extra term which is to do with this phi, which is the velocity difference, whereas before the velocity difference was 0. And again, for the record, I will write it out in full. So it's that. And finally, if you want to use that to get an equation, so it's a closed single scalar equation for n. You can't get an equation for n from it which doesn't depend on n, but you can at least differentiate down. And this, is my punchline. So if I differentiate down, what do I get? I get dn by dt is, there's the bit you can't eliminate n from, but that's the convective bit. Okay. So this thing, product rule, differentiates to give two terms. There's a dm by dx all squared, which is n1 all squared. So I take that over on the right, and there's now a kn1, 1 minus n1. And this thing is a diffusive term, so that's d by dx of d of n1, dn1 by dx, plus that. Okay, so now if I'm so minded, I can take the diffusive part of the velocity field just to be ordinary random motion. So this is linear diffusion. Here's the Fisher term that I started with. Here's the time derivative I started with, but crucially there is one extra convective term, and that term's the one that stops n1 going above 1. So it's a single extra contribution to the original equation. And that's where I wanted to stop. Thank you.
So that last equation, is that k times m times dn1 dx?
Yeah. So this is much better equation to think about because it's scalar. So this only depends on m. This one depends on m and n1. So it's not a very simple one to think about, but that is the only extra term. Yeah. Yeah.
So is there any understanding about the solutions of this set?
In strictly mathematical terms, no. So I would love it if somebody ran with some of these models.
So those lambdas are in the right corner, which take part in the interface. So that's dependent on both n and w, or
In general, but in any case, w plus n is 1, right? So the two are slaved together anyway.
because what would happen if one of my, say, n or w would tend to 0?
Yeah, so often you'll take lambda to be proportional to n times w. Yeah.
And doesn't it simplify some things in the following, or?
You get bits that cancel, so there's appealing things that happen in terms of getting back to ordinary diffusion operators and things. But I don't think there's anything terribly deep to that. It doesn't change the structure.
Okay. So I think before we break for lunch, organisers said it's lunch next. Just remains to thank John for one thing about the Engineering Institute I remember from being here some years ago, there's boards everywhere, so it's really nice to see somebody put them to very good use, and let's thank John for a lovely exposition of all these nice multi-scale multi-phase models. Thank you.